Well, good evening, students. It's Mr. Rich. It is Sunday, September 28th. It's time for another math Q&A. I'm going to take your math questions. I've got some that have come in from some of my students. We're going to take a look at those. I think we're starting with some AP Precalc questions. If you've got questions for me, you can put them into the comments section here if you've joined us live. If you're one of my students, you have my email address and you can send it to me. You know what that address is because it came to you in the invite tonight. So feel free to send in any of your questions that way. I'll keep my eye in my inbox here. And if you have any questions, we'll do it. Just a quick reminder. I am starting an SAT group this coming Thursday, I believe it is. Christina, I think we're starting it on Thursday. Yes, it's this Thursday night. It's going to run for 6 weeks up until the November test on November 8th, it is. So we're going to do 6 consecutive weeks. I do a live session of 1 hour each week, and then I give you all of the study materials and videos that you need during those 6 weeks. And there's the information there about that coming up for the November 8th test. So if you are interested in joining that, let me know. We still have room and some spots open for anybody who wants to join that group. All right, so you will get all the materials that you need to prepare yourself for the math section of the SAT for the November 8th test. All right, so let's join my screen there. So Christy, go ahead and move over to my screen. And we're going to start with what I think are some AP pre-calc problems. But if you are in Algebra 2, you'll find these interesting as well, because these are problems that you should also be able to do as an Algebra 2 student at this point. So the first question that came in, I think this came in from Corey, was an h of x function, which looks like it is definitely a quadratic equation, and it wants us to find the average rate of change of the function over the interval from -7 to 0. So in order to do average rate of change, the formula for average rate of change is going to be f of b minus f of a over b minus a. Now you might say, what's b and what's a? Well, b and a are the values of x between which you're finding that average rate of change. So it's going to be -7 and 0. And this really is an equation that you've known for several years, right? This is y2 minus y1 over x2 minus x1, because the b and the a are the two x values, and then the f of b is the y value that goes with b, and f of a is the y value that goes with the x value equal to a. So we just simply write it in function notation. So that means for this particular problem, I'm going to write it like this. It would be f of 0 minus f of -7 all over 0 minus -7. So my denominator is going to be a +7, 0 minus a -7. We do have to go into the function and evaluate f of 0. That's going to be a -4. So 0 squared plus 4 times 0 minus 4 gives me a -4. Then there's a minus, we're subtracting, and then we have to do f of -7. And that's going to be -7 squared would be a +49. 4 times -7 gives me a -28, and then there's a -4. So just doing some quick math here. This is going to be -4 minus, let's go ahead and do what's in parentheses here. This is going to give me 21 minus 4, which looks like it's going to be a +17. And then -4 minus 17 is a -21 over +7. So the average rate of change is -3. All right, so that -3 is really, it's the slope of the line that connects the 2 points on that curve, right there. Now, one of the things that maybe you want to know is how would this look if you were doing it on your TI-84? So let me show you what the calculation looks like, because if you're in AP Calc, or I should say AP Pre-Calc, you will be using this TI-84 pretty soon to do what we call regression. Now, let me reset this calculator. I think it's a little wonky here. So let's sign back in here. There we go. So what I'm going to do, just quickly show you how I could evaluate this using my TI-84 to do it very quickly and accurately. I'm going to go into the equation editor, and in y1, I'm going to go ahead and put our quadratic function. So that's going to be x squared plus 4x minus 4. So I've got the function loaded in there. I'm going to quit the equation editor and go back to my home screen or my calculating screen. And at this point, I'm going to go ahead and make a fraction on my screen, and I'm going to call up the y1 function that is holding my h of x. I'm going to call that up by doing second function trace. Sorry, that's not right. Let's quit and go back. So I'm going to go up into my numerator, and I'm going to do alpha trace. And that pulls up this menu that allows me to call up my y1 function. And I'll use function notation by using parentheses and say I want to do y1 of 0 minus, I need to call up the function again, and that's going to be -7. And then I'm going to do 0 minus -7, and then hit enter. And there's my answer, -3, that it went ahead and calculated for me. All right, so that is our average rate of change. All right, let's keep going on. I've got a few more here that came in from Corey. Let me see if any other messages have come in. It doesn't look like it. So again, if you've got any questions, if you're watching this live stream live, then what you can do is you can submit a question that you want me to work in the comments section, and I'll be happy to work it for you. Number 15 here says make a sign chart that represents the expression 9x to the fourth x minus 8 to the third is less than or equal to 0, and use your sign chart to solve the inequality. Well, this is a polynomial that they've given to us in an inequality, and what they want me to do is plot the zeros, right? Since it's in its factored form, I can determine when this function here on the left side is going to be equal to 0. It's going to be equal to 0 when either the first factor is 0 or when the second factor, x minus 8 to the third, is equal to 0. I'm going to solve both of those. This is very easy. This is x equals 0. I would divide by 9 and take the fourth root. X equals 0 is the solution. Here I would take the third root of both sides, giving me x minus 8 equals 0 and x equals 8. So what I'm going to do is I'm going to plot a point at 8 and at 0 on the x-axis. Why am I doing that? Well, because that's where this polynomial is going to be touching the x-axis. So if this polynomial is going to be going above or below the x-axis, it has to occur at one of those 2 points. So what I'm going to do is I'm going to pick a test point to the left of 0. I'm just going to use the -1. That is my test point, -1. It's going to represent all of the points that would be to the left of 0. Right? Because if -1 is above the x-axis at x equals -1, if the function is like up here, it's going to be up there for all of the points to the left because it's never touching the x-axis to the left of 0. So I'm going to use that as a test point. I'll use x equals 1 to represent all the points between 0 and 8. And then over here, I'll use my test point of x equals 9. So what do? I want to plug in my 3 test points into this expression on the left side, not to get a value, but just to get a sign, positive or negative. Well, one thing I know about 9x to the fourth, whatever I stick in for x, that is going to be positive because I'm raising to an even power. So stick a -1 in there, that's going to be positive. And when I stick a -1 in here, it gives me a -9 raised to the third power, so it stays negative. Because when I raise negative numbers to odd exponents, it stays negative. So this ends up being, when you stick a -1 in, it's a positive number times a negative number, which gives me a negative number. So that means this polynomial is below the x-axis or negative when you're to the left of 0. When we come to the right of 0, in between 0 and 8, and we plug in x equals 1, I'm still going to get a negative number because it'll be positive, and this one will still be negative. So that means it's still below the x-axis. And then this one, when x is 9, that's when it's going to turn positive because this first factor will be positive, but so will this one be positive because 9 minus 8 is positive 1, raised to third, still positive. So it is positive. So the answer to this question is, when is this polynomial negative or below the x-axis? The answer is all the way from negative infinity. It starts being negative right here all the way this way. Now, it does become 0 at x equals 0, but this says less than or equal to 0. So I can express this as one complete interval from negative infinity all the way up to and including the number 8. Now, I think it's instructive when you work a problem like that, if you don't totally, completely understand what we were doing there, it's a good idea to graph the function and say, what does this look like in Desmos if we were to actually look and see what its graph is? So let's graph 9x to the fourth times x minus 8 raised to the third power. Okay, and there we go. So you can see what's happening. The function is hitting, we zoom in here at x equals 0. The function is coming up and hitting the x-axis, but then it's bouncing and staying negative. So you can see that the function is below the x-axis, just as we said it was here and here. It does come in contact with the x-axis. We knew that because it had a 0 at x equals 0. But what happens out at the number 8? If we come out here and take a look at what's happening at x equals 8, the function is coming in and crossing the x-axis. It does a little jog there. It flattens out at 8 and crosses at 8 and then keeps going. And you can see that it does turn positive right there after it passes x equals 8. So I'm just showing you that to show you that since we don't have the technology to graph it, when we're working this problem on a test, we have to rely on this technique of plotting the zeros and then using test points between those zeros to see what the sign is, positive or negative. And then we can answer that question about being less than or equal to 0. I hope that helps, students. Let me take a look and see if any other questions came in. And if you're just joining us, my name is Mr. Rich. I am working math problems, all right? So I usually have Algebra 2 students here, or I'll have AP Pre-Calc or AP Calc students. I am going to get to both AP Pre-Calc and AP Calc problems here in just a second. What I'm going to be working, just so that you know, if you're an AP Pre-Calc student, I'm going to be starting looking at lesson 112, which has to do with function transformations. So we'll look at that, and then those of you that might be AP Calc students watching, I'm going to do a little bit of chain rule. So that's what my plan is. I think I have one more, maybe two more problems that I'm going to work here that are from really either from Algebra 2 or Pre-Calculus. And here is the first one that I'm going to work. It is a synthetic division problem. It says use synthetic division to find the result when you divide this polynomial by x minus 1. So using synthetic division is something that we do when the divisor is a linear divisor and it has a leading coefficient of 1. I do not recommend doing synthetic division when you have something like 2x plus 3. I would go ahead and back and do long division. But when it's a one coefficient linear, yeah, synthetic division is great. So what you're going to do in synthetic division is we are going to take the coefficients from what we're dividing and line those up in this box. I'm going to put this box that I'm making here, this little L. It's got 2 rows to it. The top row is going to get these coefficients: 2, -6, 11, -11, and 4. You do want to make sure that you don't have any missing terms, right? Since I'm starting at x to the 4th, I have to have a coefficient for x to the third, x to the second, x to the first, and x to the 0. And I do. If there was no, say that negative 11x was just not there, I would have to put a 0 in place of it, right? Because I have to make sure that I account for all the terms from the highest degree all the way down to the degree of 0. But we have a negative 11 there, so that is going to be a negative 11. Then what we're going to end up dividing by is when we set this divisor equal to 0, I get a 1, x equals 1. So that's what I'm going to be synthetically dividing by x equals 1 right there. And then here's the process. The process is we're going to bring down our first coefficient 2 straight down here. And so what we're doing here is we're adding vertically, and then we're multiplying diagonally. Here's what I mean. So this, since there's nothing here, you can assume that to be 0. 2 plus 0 is 2. Now I'm going to take 1 times 2 and put the result here. That would be 2. I will now add that column. Negative 6 plus 2 is a negative 4. I will now multiply 1 times negative 4, which gives me negative 4. I will add vertically. That gives me a positive 7. 1 times 7, that answer is going to go up here. That's going to give me a negative 4. 1 times negative 4 is negative 4. When I add there, I get 0. This last result, when I add that last column, that is the remainder. So there is no remainder to this division problem. So what is the answer to this? Well, the answer is that this is going to be my constant term, negative 4. That will be my x to the 1 term. That will be my x squared term, and that's a positive 7x. And then this would be my x to the 3rd term. So that would be 2x to the 3rd. So this is the result of the division of taking this 4th degree polynomial and dividing it by x minus 1. Now, you may say, well, why would we ever want to divide? Well, we usually do this kind of division when we're trying to factor, because what you just discovered by doing that division is that x minus 1 times this result that we got is the factored form, or at least partially factored form, of this 4th degree polynomial. If you wanted to keep factoring it, you might need to do more synthetic division on this 3rd degree. Okay, so that's synthetic division, and I think I'll work one more of those. Okay, so we'll do synthetic division on this one. I'm going to be dividing by a positive 1. So it's going to look like this. There's my 1. I'm pulling the coefficients off of that polynomial. So that's going to be a positive 3, positive 5, negative 11, negative 1, and positive 4. Okay, so we'll do the same thing that we did. We're going to bring the 3 straight down. 1 times 3 gives me 3. Add on the column there, 5 plus 3 is 8. Now multiply 1 times 8, and then put the result up here. Add gives me negative 3. Multiply gives me negative 3. Add negative 4. 1 times negative 4 is negative 4. And again, it turns out that we have a remainder of 0. So that tells us that x minus 1 is a factor of that polynomial. Now, interpreting the answer, what is the answer to the division? Well, again, that's going to be the constant term. That will be the x term. That will be the x squared term. And the 3 will be the coefficient for the 3rd degree term, 3x to the 3rd. And there you go. That's your answer to that polynomial division. All right, well, if you are watching, if you've got a math question, send it to us in the comment section, and I'll be happy to work it. If you're one of my students, it's easier to just email me. You've got my email address because it went out to you in the invite that I sent to you yesterday and today. I'm looking. I don't see anything that came into my email. So what I'm going to do is I am ready because I know what questions you might have if you're in AP Pre-Calc. Most of my students that I work with that are in AP Pre-Calc are starting lesson 1.12. You took your test or your summative on 1.7 to 1.11, and now you're getting into transformation of functions. If you're an Algebra 2 student, this will be of interest to you because you are also doing transformation of functions. You're not doing it to the extent that the AP Pre-Calc students are, but you are going to be doing these kinds of things. So let's talk about it. So the first thing that we're going to do is we're going to talk about translation of functions. But really, even before I show you this, I want to remind you of the different transformations in AP Pre-Calc that you have to know how to do. So I'm going to go ahead and make a list of those here. And then I'll point out the ones that apply to most of the Algebra 2 problems as well, so that you Algebra 2 students. So the first thing is that if you have a function f of x, and it has a graph, it has an equation, and you want to shift it vertically. You want to take the whole graph and go up or down by a certain number of units. If you take your function f of x and you add 3 to the end of the function, you're going to cause the entire graph to go up by 3. It's what we call a vertical translation. If you did a -3, it would go down 3. I mean, the whole graph would just shift down by that many units. It makes perfect sense that that's what would happen. And I'll show you some of these examples over in Desmos here in a minute. If you take a function f of x and you want to move it horizontally, left or right, what you have to do is do this. You have to replace all of the x's in the function. Let's make it x minus 4. If all of the x's in a function are pulled and replaced with x minus 4, right, that's what this notation means. The x's become x minus 4s. What you're going to do is shift it to the right by that many units. Now, you may be thinking, wait, Rich, I think you have that backwards. Wouldn't that be left 4? Well, you would think so. Or common sense would tell you that maybe it's left 4. It's not. When it comes to these horizontal translations, it's maybe the opposite of what you would think it would be. So x minus 4 means a right 4. If we did f of x plus 2, that would make a shift left 2. Now that one I am going to show you what this would look like over in Desmos. So what I'll do is I'm going to make just some random function here, and I'm going to do a polynomial. Let's do a random third-degree polynomial. So we'll do x cubed plus 3x squared minus 5x. Let's see what that looks like. Okay, there it is. And we'll spread this out just a bit. Now, what I'll do is let's copy that, and we'll put it down here. Now, let's tack on plus 5. So you can see that the whole function, everything on this function moved up by 5 units. That point right there is now up here. Same x value, but now it's 5 more. That y value is not 15.7, it's now 20.7. So it shifted it up by no big deal. So that just simply tacking on an extra term plus or minus causes that vertical shift. However, it's a little bit different if I want this thing to go left or right. Let's suppose we want the whole thing to go left 2. What I would have to do, if I want to go left 2, I have to pull all the x's and replace them with x plus 2. So that x becomes an x plus 2. This one, notice I'm putting them in parentheses because the x is getting pulled and replaced with x plus 2. All of them did, like that. Okay, so I just transformed the function according to f of x became f of x plus 2. Now let's see if that's legit. I'll turn that function on and see if it doesn't go left 2. Okay, it does. So you can see that that resulted in a shift right here, maintaining that y value, 15.7. That's a negative 4.63. So it perfectly shifted the entire graph of the function left 2 units. All right, so those are the vertical and horizontal shifts. So if you're working in Algebra 2, you have to know how to do those transformations. Let's do vertical stretch. Suppose we take f of x and we put a multiplier in the front of the function. Okay, that is what we call, and this is the verbiage that we use in AP. We call that a vertical dilation by a factor of 3. And here's what you need to know about it. What does that mean? Vertical dilation. We sometimes in Algebra 2 will call that a vertical stretch by a factor of 3. It's like we're taking the whole function and we're just making it go 3 times as high and faster. We're just vertically like stretching it like a rubber band. But really what it means is every single point that's on the graph is going to be 3 times as far away from the x-axis. Any points that are on the x-axis aren't going anywhere because there are no distance from the x-axis. But anything that's not on the x-axis will become 3 times as far away. Right? You could also do a vertical dilation by a factor less than 1 by, say, putting a 1/2 instead of a 3. That means it'd be like a vertical shrink, but it'd be a vertical dilation by 1/2, meaning the distance of all points to the x-axis gets cut in half. It's kind of like you're taking it and squishing it and compressing it. A vertical compression, sometimes it's called. All right, so and that is also something that you have to know in Algebra 2, those vertical dilations. The next one would be when we do a reflection and put a minus in front of the function, which means we're really multiplying the entire function by a -1. We're putting a negative in front of the entire function. That will be what we call a reflection in or across. They call it really in the x-axis. You're doing a flip around the x-axis. All right. Now, I'm going to give you 2 that we don't really emphasize in Algebra 2, but are going to be emphasized in AP Precalc. And that is when we do a horizontal dilation. So if I take f of x and in front of all of the x's, I put a 2, make it a 2x. What that is that is a horizontal dilation, but not by 2, not by a factor of 2, by a factor of 1/2. Okay. So if I replace all the x's with 2x, what I have done is I've taken the whole graph and I have squished it like an accordion, and all of the points have become half the distance to the y-axis. So the whole thing came in and got sucked in closer to the y-axis. In this case, with that 2, it would have been cut by a distance of 1/2. If we did f of 1/2 x, that would be a dilation by a factor of 2, which would then be like a horizontal stretch, as I made all of those points on the function to be twice as far from the y-axis. All right, and then the last one is when we replace the x with a negative x. And as I'll show you, we have to be able to do these things, multiple transformations on one function. But when you put a negative in for all the x's become negative x's. What you are doing there is you are reflecting in the x-axis. Excuse me, reflecting in the y-axis. In other words, all the positive x's become negative. So you're flipping the thing around the y-axis. So the stuff that was to the right of the y-axis, all those points are going to an equal distance, but on the left side of that y-axis. All right. So those are the transformations. Now, what we do in AP Precalc is we start off with these piecewise functions, and we want you to learn how to do the transformations this way. These are pretty straightforward. I'll just do a few of these. So if you were given a graph of f, so the red line that you see here is the function f. And the g of x is what they want you to graph. And it is the function f of x that's been vertically translated down by 4. So what I'm going to do is I'm just going to take the key points that are on this graph. And by key points, I'm talking about these these endpoints. we'll take the middle of the circle up there. And all 5 of those are going to get shifted down by 4 units because it's f of x minus 4. So this point's coming down here. That point's going to come down to -6. So I'll redraw that line. This one's coming down to -4. We got that. That point is at 1, but when it shifts down by 4, it goes to -3. That one comes here. There we go. So that's my sketch of the function that's been translated from g of x to f of x minus 4. All right, let's go to the next one. All right, check and see if any questions came in. There are no questions. Okay, so these are going to be vertical dilations. And here's what we're going to do. What I want to show you on these is multiple transformations. So there is a function, f of x, and they want me to graph g of x that undergoes those transformations. So I'm going to do 2 things. The 3 multiplier is a vertical dilation by a factor of 3. So all of the points are going to have to get 3 times as far away from the x-axis. But then after I do that, they're all going to also get shifted up 2 units because there's a vertical translation of 2. So let's do those 2 things to each of these 5 points. And by these 5 points, I'm talking about these 5 critical points. So what will happen is this point, which is at on the x-axis, when I vertically stretch by 3, it goes nowhere because it's 0 units away from the x-axis. So 3 times 0 is 0. But it does get shifted up by 2. So it'll be right there. This point is 2 away from the x-axis. So it's going to go 3 times as far away down here to -6. But then it gets shifted up by 2. So it ends up right here. So that first segment becomes this segment right here. Let's go to this third point. And again, just like the first point, it doesn't go anywhere from the vertical stretch because it has no distance from the x-axis, but it will get shifted up by 2. So it's going to go there. And then, therefore, I'll connect those 2 lines. And I do that. This point will get vertically stretched by 3. So it's 1 away from the x-axis. So it's going to go 3 times as far away. So it's going to be up here, but then it's also going to go up 2 units. This point, like the other points on the x-axis, doesn't respond to the stretch, but it will go up by 2. So then this is like no longer a semicircle, right? This is kind of like more looking like an ellipse, kind of a stretched circle. But that's what that would look like. That's the new graph, g of x, that has undergone those 2 transformations. Let me show you a few other things in 112. Let's see if I can find one. Not quite. We want to look at domain and range. Let's see if I can find it. Maybe up here. Yeah, here we go. So this tells us about a graph F who has a domain of -4, 3, and 3, 9. And you can see it's inclusive on the endpoints of the domain of -4 and 3, but exclusive on the 3, 9 with the brackets and the parentheses right here. And then, but g of x is a transformed version of f of x, and it undergoes those 3 transformations. So let's list out those transformations starting at the inside here. So replacing x with x plus 5 means that all of the function points are going to move left 5. Then that minus right there is going to reflect across the x-axis. And then lastly, there's going to be a vertical translation. We'll say up to. Now, what we want to do is categorize each one of those transformations as to whether it's going to be affecting the domain or the range of the function. So when I take a function and I shift it left or right, that's not going to affect the y values at all. So it will not affect the range, but it will affect the domain. Well, when I reflect things across the x-axis and I flip them around the x-axis, that's not affecting any of the x values. All that's happening is the y's are changing signs. And then shifting something up by 2, again, doesn't affect the domain. So these two are affecting the range. So what I can say is that the new function g of x, I know what its domain is going to be. It's going to be that interval shifted left 5. So if you're at -4 and you go left 5, you end up at -9. At 3, go left 5, you'll end up at -2. So that would be the domain for this new function g that's been transformed. Let's affect the range with these two. Well, when we reflect across the x-axis, the y's are changing signs. If it's a point here, the lowest point is 3. Well, what that means is that the highest point is going to become -3. And if the highest point is 9, it's going to reflect and become the lowest point at -9. So that's what happens when you do the reflection across the x-axis. But then we have to shift it up too. So there's one more change that we have to make to the range to get to our final answer for range. We have to go up 2. So the -9 will go up 2 to be -7. The -3 will go up 2 to become -1. So our final answer is the domain will go from -9 to -2. The range is going to be going from -7 to -1. All right, well, that is kind of the overview of what you have to know for translations, or what we would call, generally speaking, transformations of functions. And the way they split it up in the AP curriculum is they call them, in the first part of 112, they refer to them as translations. That's where you're moving things left or right, and then, or maybe reflecting. But then the second one is going to be when you are dilating the functions. That's where you're applying the multipliers that are in front of the function for the vertical dilations, or you're putting a multiplier in front of the x's, which then causes it to be horizontally dilated. Well, that is going to be it for AP Pre-Calc. Let's switch gears and go to AP Calc. A few things that I want to show you here. This is the chain rule. I wanted to talk about how we use the chain rule to take derivatives of functions. So let's start with a function here, and let's talk about why we need the chain. If I were to take the derivative of this polynomial, 3x minus 2 to the 4th power, what I would really have to do using the rules of derivatives that we've learned up to the chain rule is I would need to expand that polynomial all the way. Now, we could do that. We could do it pretty easily using Pascal's triangle and binomial theorem, but we don't want to do that. How often do we use the binomial theorem and Pascal's triangle? Not very often. Okay, but if I were to take the derivative without the chain rule, I would have to do that first. But here is what the chain rule allows us to do. It says this, that I'm going to give you the definition of the chain. Your teacher has probably shown you. If I take the derivative of a function within a function, what we have always called through Algebra 2 and Pre-Calc a composition of functions. In other words, I have a function within a function, and I want to take the derivative. What we do is we take the derivative of the outer part, so I'll call it f prime, and leave the inside part alone. then once I take the derivative of the outer part, I need to multiply that by the derivative of the inside part, g of x. Now, a lot of students, when they see this definition, they're like, I don't even know what you're talking about. When do I ever see f of g of x? Well, we're looking at it. We're looking at one right here. This would be the composition of functions where one of the functions f of x is x to the fourth, and the other function g is 3x minus 2. Because f of g of x would mean you're sticking the 3x minus 2 in for the x, right? So back in Algebra 2, we used that crazy function composition notation there with like that little circle that looks like fog of x. And your teacher probably told you that what that means is just a notation that really represents f of g of x. And students, if that's my f and g right there, and I tell you to do f of g of x, you would say, all right, the x in the f function needs to be replaced with 3x minus 2. And then it's no longer x to the fourth, it's the entire 3x minus 2 raised to the fourth power. So if we want to take the derivative, according to this, what we can do to take the derivative of this function right here is, we don't want to see the news. What we want to do is we're going to take the derivative of the outer function. The outer function is this entire thing right here, and I'm going to use the power rule. So I'm going to take the 4 to the front. I'm going to leave the inside part alone, 3x minus 2. By the power rule, we reduce that exponent by 1. It becomes 3. But then we have to now multiply by the derivative of the inside part. The derivative of 3x minus 2 is 3. So this is what it looks like using the chain rule. Again, I'm really showing you what the derivative is down here, y prime, down here, from our function y equals 3x minus 2 to the fourth. It's this. This is the derivative of the outer using the power rule. This is the derivative of the inner, 3. And then we could, of course, write this as y prime equals 12 times 3x minus 2 to the third power. So that is the chain rule. Now, in practice, we don't really need to think about, defining f and g and thinking about this. We just know that it's the derivative of the outer times the derivative of the inner. And you just need to get some practice. And I'll show you some examples. I'll try to work as many here as I possibly can. And I'm going to work a few challenging ones. Let's start off with this one. Okay, 6 plus 3x all raised to the 2/3 power. So I do know that I have a function within a function. So using the power rule, that 2/3 exponent comes out to the front. I leave the inside part alone, and then I'll reduce that exponent by 1. So I'll take 2/3 minus 3/3, which gives me a negative 1/3. And then I will multiply that by the derivative of the inside part, which is just 3. I will clean that up just a bit because this 2/3 is being multiplied by the 3, which will make that just a 2. And at the same time, I'm going to push that negative exponent down into the denominator of my answer and then change that to a positive 1/3. All right, so you got to know your rules of exponents here. Right? If you don't have rules of exponents nailed down by the time you're in AP Calc, it's going to be a problem. So, and you got to be able to do fraction math on the fly, right? You got to be able to take 2/3 minus 1, 2/3 minus 3/3, negative 1/3. Got to know that negative exponent. How do you get rid of a negative exponent? Push that factor down into the denominator and change the sign on that. Okay, let's move on. Let's do one with trigonometry. Here we go. I've got the sine of e to the 2x. Now, this one right here, students, is what we would call a nested chain rule. This is going to require me to use the chain rule twice, because not only do I have an e to the 2x inside of a sine, but I have a 2x inside of an e to the x. But here's how I'm going to handle this. Now, what I tell my students is this. What is the derivative of sine of a thing, sine of something? Well, it's cosine. So the very first thing I'm doing is just saying, all right, fine, I'm going to take the derivative of this outer function. In other words, I don't care what this inner part is. The derivative of sine is cosine. And I'm not going to touch the inside part. Like that. So the derivative of sine of something is cosine of that something. But now I do, by the chain rule, I do need to multiply by the derivative of that inside thing. And the derivative of e to the 2x is itself e to the 2x, but times the derivative of its exponent, which is 2. So I just used the chain rule twice. The derivative of e to the x, as you know, or you're supposed to know at this point, when you take the derivative of e to the x, it is its own derivative. But if you're taking the derivative of e to a function of x, you have to, sure, leave it, it's its own derivative, but you then have to follow it up with the chain rule by multiplying by the derivative of that exponent. And so you could clean this up maybe and take the 2 e to the 2x to the front times the cosine of e to the 2x, and that would be the derivative. All right. I want to show you this problem here. If you are going to take the derivative of a sine squared, you have to know what sine squared really represents. I am going to rewrite this, not doing any calculus here or algebra here at all. I'm just rewriting this as to what this really means. Sine squared of pi theta is sine of pi theta all to the second power. That's what it is. Okay, so that's what sine squared means. Now I can more or less recognize this as a chain rule by using the power rule to start with, because I've got something raised to the second power. When I got something raised to the second power, the derivative is going to be found by taking that exponent times the coefficient in front, which is 8. I'm going to leave the something alone, and then I'll reduce that exponent by 1, so it becomes a 1 power. So I'll just leave it as that. But then I have to multiply by the derivative of this inside part. And the derivative of sine of something, I'm using this word of something because the inside part doesn't really matter when I'm taking the derivative of the outer part. Right? The derivative of sine of something is cosine of that something, right? So it's cosine of pi theta, but then I have to multiply by the derivative of pi theta. See, theta is my variable. So when I take the derivative of pi theta with the power rule, the answer is just pi. It'd be like saying, what's the derivative of 3x? It's just the number 3. Take the derivative of 3x is 3. The derivative of pi times the variable theta is just pi. So that right there is the full expression for the derivative using the chain rule twice. I had to use it twice. So it ends up being g prime of theta is, I'll move this pi to the front and do this as 8 pi times sine of pi theta times cosine of pi theta. Okay, and that is the chain rule there. And I do want to show you another one. I think I want to come in here. Yeah, that's tables and graphs. Or do I want to do? No, I think I still want to do one more that's up here. Let me find out where it is. I think it may be up here. Yeah, I want to show you this one. This is what it was, because this requires me to use all the things pretty much. I need to take this derivative, I have to use the product rule and the chain rule. And here is what happens. Let's go ahead and rewrite this, changing that radical to a fractional exponent. So it's going to be 1/2 x squared. This will be 4 minus x squared raised to the 1/2. So my first function is a product rule, because I've got two functions being multiplied. I have a 1/2 x squared, and then I've got this 4 minus x squared raised to the 1/2 power. So remember what the product rule says, that if you're going to take the derivative of two functions of x, we'll call them f and g, you take, this is my formula that I use in this order, right? I take the derivative of the first one times the second plus the first times derivative of the second. So I leave them in the same order, f and g. I just flip the derivative. I take the derivative of f first, but then I take the derivative of g second. So what I'm going to do is, when I do this, take y prime, my derivative, I will take the derivative of 1/2 x squared, which is just x, using the power rule. And then I have to multiply that by 4 minus x squared to the 1/2 power. Then what I'm going to do is put a plus sign, right? Because the power, or excuse me, the product rule is a plus sign here. Then I will take the first function, 1/2 x squared, times the derivative of the second function. And my second function is the 4 minus x squared to the 1/2. So I'm going to start this with the power rule, because I have this thing, 4 minus x squared, raised to the 1/2 power. So that means I would be multiplying by the exponent 1/2. I would leave the inside alone, but reduce the exponent by 1, so it becomes a negative 1/2. And then I would multiply by the derivative of the inside part, which happens to be negative 2x. That right there is the derivative of y using the product rule along with the chain rule. So just to recap what's going on here, this was the derivative of the first times the second plus the first, and this whole thing was the derivative of the second function, which was the square root of 4 minus x squared. That's what we got, this whole thing right here. Now what I'm going to do is I'm going to clean this up just a bit. And I don't think we're going to have time to do all of this, but I'll show you a little trick here. The 1/2 times 1/2 is 1/4, times the negative 2 would be negative 2/4 or negative 1/2. So this is going to be a negative 1/2. I do have this x times this x squared, so that will be an x to the third. And then I have a 4 minus x squared to the minus 1/2. Now the challenge that you have here, and that you'll be facing here in the next month in your AP Calc class, is how you are supposed to write this as one rational function, because you do have a radical here down in the denominator. That minus 1/2 will get pushed down into the denominator. So you would have to write this as one complete fraction. I'm going to show you. I'm not going to be able to work it all here tonight, but what you would do, or what the way that I would recommend doing it, is you're going to factor out the greatest common factor between these two terms right here. Because remember, all this is being multiplied. So that's one complete term. What I'm going to do is recognize that I can pull out a 1/2, whatever fraction I have here in these two terms, I'm going to pull that out. I got an x and an x cubed, so I can pull an x out. And they also have a 4 minus x squared that's in common. And I, as always, use the smallest exponent in my GCF. So 1/2 minus 1/2, that smallest exponent is a 1/2. Then what's left inside, after you pull that out, is found by division. Always when you factor out a GCF, to get what's left in the parentheses, you're going to divide these. You're going to divide each of these terms by the GCF. When I divide this whole thing, 1 divided by 1/2 makes it 2. And then what's going to happen here, the x's will cancel, so that x will go away. And what I will have is 4 minus x squared to the 1 power, because this divided by this would cause me to subtract those exponents. And 1/2 minus negative 1/2 is 1. Over here, what I have left is the 1/2s will cancel. X cubed over x leaves me an x squared. And that's all that I have, because this got knocked out when I divided it by that. So what that allows me to do is it does allow me to say, I think I missed one part of this. Maybe not. But what this allows me to do is it allows me to take this factor and push it down into the denominator and leave me with one complete rational function. Because this part will be my numerator. That's going to leave me also an x up here. And then this 1/2 means there will be a 2 down here. And then this would be 4 minus x squared to the 1/2. Right? Because that factor can go down into the denominator. So that is kind of a trick that you could use to get this expressed as one complete rational function. But that is way beyond the chain rule at this point. We just want you to be able to use the chain rule and learn to use it. This was the algebra manipulation that's coming down the road here shortly. So you got to be good with your algebra and factoring. And that, students, is all we have time for tonight. So we'll leave it at that. So next week, we will be back here again taking your questions. And remember, I did want to remind you, I do have an SAT group that is starting this Thursday night at 8 o'clock. And we're going to run for 6 weeks. I'll do a 1-hour live session. We're going to hit all of the 4 domains of the SAT math section. I will also be providing you, if you join our group, I'll be providing you the study materials that you need. I have a third-party package that I use, and it is outstanding as far as how it lines up with the actual SAT math questions. So I'll be happy to have you join our group this coming Thursday. If you need information, you can take a look at my email, which I think will pop up here in just a minute after we get done. Okay, everybody, I hope everybody has a great week, and I'll see you next week for another math Q&A. Bye, everybody.